Hi, my name's Dan, and this video is, I believe, the last in a very long series of 55 videos in which I have charted the progress of using this software, Digital Works, which is a digital electronic simulation software, and is free to get hold of and use. You could use it yourself. There's a link in the description down below. Um, where was I? Yes, I'm using this software to create a 4-bit working programmable CPU from the basic logic gates that we all know and love. Or if you don't know and love, then I'm not sure what you're doing watching this video. Um, we've been on a long journey and we have created lots of components. We've talked about what they are and how they work. There's been hopefully a lot of learning going on if you've been following through. And I hope you've also been following through, playing along with me, making this CPU in this software. At the end of the last video, we did a very quick test to see if it would retrieve one command and make it execute, and that seemed to work. So we seem to be in a place where we have a working CPU. This video is going to go through the process of creating some simple programs in order to test the CPU out. I may record it in small sections, do several different programs. We'll see where we go along. I'm not entirely sure where I'm going to go with this. But what I have done is I have written a first program, and what is going to happen is I'm going to flick backwards and forwards between Notepad and the digital simulator quite a lot as I try and work out what my program is and what needs to go in. So let's bring that up. I've got OBS running as well, which is the software that I use for actually doing the recording, but everything else is hopefully turned off. So as I flick, you shouldn't be seeing things that shouldn't be there. So this program I've written it out like this so that we've got the address, so the sequential addresses. I've written the actual code that I need to put in. A couple of these need data. And then I've also written something that tells you what the opcode does. And what this particular short, they're all going to be short, program does is it should add the number 3 and the number 10 together, and the output should be 13, obviously. So in order to get a number into the B register, we need to put a number in the A register first and then transfer it from A to B, because we have limits to the number of opcodes we could have. That's why we can't write directly into the B register. So I'm putting 3 in A, and then I'm moving, copying A to B, and then I'm putting 10 in A, and then I'm doing A plus B, and then I'm going to move the result from ALUX back into A. And one of the reasons for that is that we don't actually have on ALUX a visual output to show us what the result of a calculation is. So that's going to test several opcodes. We've already tested 0000 for Hull. We know that that works, which is great. And one of the reasons for designing this program the way that it is that actually once I've entered this in, I should be able to just change this one to different arithmetic codes to see if they work and to get different results. So I should be able to actually test all of them, maybe all but one. Not quite so sure. We can do the comparison test. We haven't got the jump in yet, but we'll deal with that later. And the one thing that I want to make sure that I'm doing is that I am over however many programs we're going to run, making sure that every single opcode has been used. So the first phase is to check all these arithmetic operations, and we'll see where we go. Right, I'm aware that we haven't got LEDs on the C out and the Z, Actually, we are going to be able to see the results of those because they do go dark if they're high. It's just easier to see with LEDs. In fact, I didn't really want to add to this whilst we were uh, programming, but I am just going to chuck in a couple of LEDs for C and for Z because it is slightly more visual. Okay, and I'll do another save. Right, and I was running there, so I've just stopped and restarted running. So the first thing I need to do is a full clear. Oh, we're running. Let's turn run off. Do a full clear off. So that should have cleared all the memory out. And we're going to start flicking backwards and forwards. So we're going to enter manual entry mode and 0000 for the address, 1101 for the op, and 0011 for the data. 1101 and 0011. 1101 and 0011. Okay. And write to data memory. Switch off write to op memory. Okay. And then we'll go to the next address. Make sure that those two writes are off before I change the address. And in 0001, we need the code 1011. We don't need data. 1011, 1011, write to our memory. Let's get the next address. 0010 is 1101, as we've had before, and we want 1010 in the data. So 1101, that's the one that's going to be harder for me to remember. 1101, write to our memory, and 1010, write to data memory. Those are switched off. I go to the next address. 0011 is 0010 in the op memory. 0010, which is the inverse of this. Right to op memory. And then finally 0100 address is 1110. 0100. Remembering all these things is can we think? I could have made another macro and written this out and stuck it down here or something, but I couldn't be bothered. But I now can't remember what that code was that I needed. 1110. 1110. Right to op memory. Those are switched off, and that takes us out of manual entry mode. Okay. Let's make sure we do a reset where our program counter's at 0 anyway, but our latch maybe should be on. But let's do the reset anyway. There we go. And then let's run. So let's predict what the end result should be. It should be 13, which is an 8, plus a 2 plus a 1. No, that's 11. An 8 plus a 4 plus a 1. So it should be 1101. Is that right? In 13, and it should end up back in A. Let's run and see what happens. So we're fetching the first command, which then should have put 0011 in our A register. We're now transferring it to the B register. That's happened. We're now putting 1010 in the A register. There it is. It's appeared. We now should be adding the two things together. So we should see nothing particular as a result here. And then we're taking the result from ALU, and we should be putting that in the A register. And we've got 1111. And then we should be stopping. Halt. It was always going to halt at that phase there. So, is this correct? It is. It doesn't look correct because it looks like we've got 15. And I thought we should have 13. So I've done an edit at this point because I needed some time to work out what was wrong. I dove down into various parts of the program. I rechecked it. I had a look in the ALU. I've added some LEDs in here to see what was going on. I was diving further down here into the adder. I even got down into here and was looking at the adder because the result from the addition just didn't seem to be correct. And in fact wasn't correct, as you saw. Um, However, I have found what the problem was, which was my wiring here was not right, and I had wired incorrectly out from A into the ALU. Um, so it was obvious, obviously that was why it was going wrong, because I was not feeding the right number in to be added. So let's try this program again from the start. I'm still running the simulation so that the actual data, the program should still be in the memory. I'm just going to do a reset. I have just done one of those, and then I'm going to run, and then let's talk through it working. Hopefully it'll work this time. So we're taking the number 3, it's gone into data, and it's gone into the A register. And then we're moving that, so this is the, into B, this is the second command. And then the next command should be taking number 1010, which appears in data and has now appeared in the A register. This next cycle, here we go, is actually doing the addition now. And then the next cycle should be bringing that out of the ALU and putting it into A, which is that is the number that we expected, 1101, which is 1010 add 0011. And then the last cycle is the one where it stops. So hurrah, it's working. We've written our first program and it's actually done what we wanted it to do. So now let's check A minus 1. So what we're going to do is we're going to leave this program as it is, apart from changing um, the operation that actually does something. So this is the one that's in the address 0011. When we're just doing something on the A, it means it's going to do some stuff with B that is not relevant. But that's okay because it's less work to just leave the program as it is and let it run through with this moving the 3 into the B before it does something with the A than it is to keep rewriting all of this. So I'm just going to rewrite this code here over the next few iterations and check that our ALU operations are all working. So the next one I'm going to do is A minus 1. So A at that point will be 1010, so it should give us 9, which is 1001. So our memory address for entering this is 0011, which is already in there. I'm going to take run off, otherwise we're going to have a problem. Go into manual entry mode, and the operation we want is 0001, 0001, and write that to op memory. Okay, and then we take the manual entry mode off, do reset, and then run. And this is now our second program. So as before, we've put 3 in the A register, and then we're transferring that to the B register. There we go. And then we're going to put 10 in the A register in the next cycle. There we go. 10's moving in. It's in the A. And then the next cycle is going to do A minus 1. So this is where the execute goes on the ALU. You can see that happen if you're looking closely. And then we're going to transfer the result out into our A register. And there it is, 1001. Perfect. And then it just goes a few more flicks and then stops. Right. So let's try A plus 1. So that's 0100. Switch off run. Switch on manual entry mode. And what did I say it was? 0100. 0100. Write to op memory. Take manual entry mode off. Do a reset. And run. There's our three that we're bringing in. It's interesting. It kind of these they trickle down. It comes to the memory bank, and then it comes to the data register, and then it comes to the A register. Anyway, that's copied it to the B register. If those had been the other way up, it would have trickled all the way down. There we go. That's our 1010 into our A register. Watch the execute line on the ALU. There we go. Um, that's actually done the calculation, and now we're copying out from the ALU out to A. And we've got 1011. Is that what we expected? Well, 1010 add 1 should be 1011, which is 11. And we've stopped. Right. Let's do A minus B. I've deliberately chosen numbers where this works. So B is going to be 3 and A is 10. And so our result should be 7, which is 0, 1, 1, 1. So back we go into our manual entry mode. And the opcode is 0, 1, 1, 1. 0, 1, 1, 1. Right to op memory. Okay, let's take us out of manual entry mode. Right, so let's do a reset and then start running. So A minus B, quick reminder, it should be 7 as the output. That's our 3 got into A, and then that should move up to B in this phase, this round, which it has done, and then we should get our 10 into A, 10, 10, 10. There we go. And then we should get the execute on the ALU should go now. There we go. And we've got a C out lit because we've got an overflow because it's a subtraction. And there's our result, 0, 1, 1, 1. And then we're just going to stop now. Okay. Right, what's next? Inve. So run off manual entry mode, and it's 1001. So the inverse of 1010, which will be what's in there, should be 0101. Right to alt memory. Manual entry mode off. Reset. And run. Same process as before. 3 is coming down into A. A should be going up into B. There we go. 10 coming into A, comes into the memory bank first, then the data, and then into A. There we go. And then the next cycle will be when we do the calculation. That should be hit, and C out has happened. And then our result, 0101, which is, again, what we suspected, or expected. So the last one, A equals B, which is actually does A XOR B, and we'll look at the the Z out to see whether they have been the same. Do we want to check something to check the Z outs, or should we just see what the result is? So what is A XOR B? If we've got 1010 and 0011. So that should be 1 for the most significant bit, 0 for the next significant bit, 0 for the next significant bit, and 1 for the final output. So it should be 9, 1001. So let's check that, and then we'll check the Z by changing one of those values. So 1010 is the thing we need. Let's turn off run, turn on manual entry mode. 1010, right to op. Let's double check that. Yes, right to op memory. Turn off manual entry mode. Do a reset. My prediction was 1001. I've done that in my head as an XOR, so I might not be correct. There's the 3. There's the 3 into B now. And then the 10's coming into the memory bank, into the 4-bit register, sorry, into the data register and into A. Then the calculation is done now. There we go. And then the results should be transferred now. And it is, as we predicted, 1001. Let's flick back to the program, and we're going to change the first number to 10. So that's at address 0000. We're going to give it the data 1010, and then we're going to compare A and B. We didn't actually have to put it in twice, but we're still kind of keeping the structure of this program. And then hopefully we're going to see the Z out. In fact, what I'm going to do is I'm going to put in a jump as well. So let's write this in, and let's check 0101 is going to be. Let's alter this first. This is going to be interesting because it should jump when we're not 0. So jump not 0. Which one of those is this? 0110. 0110. So this is a new thing that we've got to add. We're not alter as we've had higher up yet. So jump not Z. And where should we jump to? Well, we should jump backwards if we want to loop, or forwards if we just want to demonstrate the jump and jumping out. Tell you what, let's jump back to the start. Okay, right, so we want to add in 0101 for the address and 0110. Can I remember that? 0101, 0110. Oh, and zeros in the data memory. Right, let's take run off. And the address was 0101. The data was 01, sorry, the opcode was 0110. Let's double check that. In here, that's 0110 is jump not Z, yes. We need to be in manual entry, data entry mode. Right to op memory. I want 0000 here to write to data memory, although it should already be zeros. Okay. So if this is not a Z, so there's a not a 0 output, it should jump to 1111, which we should see appearing in the address up here. Okay, let's do a reset and a run. So we're still bringing the 3 in, and we're still transferring that to B. And then we should still be bringing the 10 in, going to A. And then this is the one where we do the compare. There we go. And this is the one where we take the result and put it in A. And then this is the jump. Okay. So that should have put 000 in the program counter. And it has. We've gone back to the beginning, and it's keeping running. So we're going to stop running. So we've stopped it running, and we're going to alter our program again so that we've got 10 coming in. So this time it should not jump, and it should just run off the end and stop. Okay, so the thing that we need to change is at address 0, we need the data 1010. So run is off, manual data entry mode, 1010. Make sure we've got the right address before we write to data memory. There we go. Take that entry mode off, do a reset, and run. So that's now got 1010 put into A, and copy it up to B. Now, and then we're going to bring it back into A, even though it's already in there. 1010 into A. And then we're going to do the compare, and we should see the Z light go on. There we go. Z light's gone on, and this should mean that the jump doesn't happen. And we're watching the program counter. At the moment it's 1001, and it should go on because it hasn't jumped. There we go. 0110, and this should stop now in the right place. Excellent. So we've tested all of the arithmetic stuff. I think it would be worth testing some of the data movement things. So let's devise a program to do that. Let's stop the simulation running first. And in fact, at this point, let's do a full clear because we're going to write a different program. So we have already tested putting data in A. We've already tested putting A into B. Okay, so that's a couple of these data transfers tested. Let's. I've just seen an error on my set of opcodes, which is you've probably seen this ages ago. Because I've got halt up there, but I've also got halt on this one here, which should be a reg because it's a reg transfer. So let's get a number and start moving it around. We might want several numbers. So let's use 7. So that means let's put 7 into A. Okay. And then let's put A into B. That's fine. And we've got to delete from there. This is our addresses, so we need to keep those straight. Let's clear. No. We can go to memory and then pull back from memory. We've done ALUX into A. We haven't done B into A. We've done data into A. We haven't done a memory location into A. We haven't done A to a memory location. We've done A to B, but we haven't done B to A. So let's use our numbers 7 and 10. And let's put, we've moved 7 into A, and then we've moved A into B, and then we're going to move 10 into A. So this is 1101 as was at the top. We're going to use 1010, so that's transferring the number 10 into A. And then we're going to move that into a memory location. So how do we do that? A to a memory location is 1. Sorry, I want the address first, 0011. And the opcode is 1000, 1000. And we're going to put it in the data location. We're going to put it at the top of the memory. So let's put it at 1111. No reason why not to put it out of the way. So that should mean we're putting A into 1111. And what we'll do then is we're going to test transferring from B back to A. So leave the address. In fact, let's put several addresses in so we can stop thinking about those. Right. So let's go from B to A. B to A is 1111. Okay. Get this the right way around. And then let's do the transfer from the memory back to A. So what this should do is we've got two values and we're kind of shuffling them around, but it should show each of them changing. So we'll use the memory location 1111 again. So we'll retrieve that number back. So A should go, first of all, should be 7, then that should be shoved into B, and then should be 10, and that's shoved into the high memory location. Then it should go back to 7, and then it's going to go back to 10 as we draw it out of the memory. So we're going to go 1100, which is to draw out the memory, and the memory location is 1111 again. And this is the contents of 1111. There we go. So we didn't need those two, but we're going to leave those. Might want them later. So we're going to write this program into our memory using the manual data entry. So first of all, we've got op 1101, and the data is 7. Okay. So manual entry mode. We're at 0 first, and we want the data 7. And what was the opcode? It's data to A, so I can just check it from here. 1101. 1101. So I need to make sure I do that and that before I move on. 0001. So B to A, 110, no, sorry, 1011. 1011. Right to op memory. And the next is 10 into A, so it's 1101 again, and 10 in the data. So I need the next address. 10 in the data, right to data memory. And the opcode was 1101, I believe. I'm just double checking that again. Data into the register. Okay. Let's write that. Okay. Next address. We're going to move it into the high memory address 1111. So it's 1000 for the op and 1111 for the data. 1000 for the, how I incremented the address. 0011, that's correct. Yes, so right to op memory. And 1111 is our location. So write that to do some memory. Right. Next address. Let's try and make sure we change the address as the first thing that we do, just to make sure we stay right. Right, so the opcode is 1111 because that takes B to A. 1111 code, and then the final entry should be 0101 for the address, 1100 for the opcode, and all ones for the data. 1100, 1100 for the opcode, and all ones we've still got. Can write that to memory. That hopefully is it. Let's take off the manual entry mode, do a reset, and run. So, first of all, we've got 7 coming in, and that comes down to A. Now that should be moved up to B in the next cycle. There we go. And then we've got 10 coming in the next cycle. Down into A. Right. The next cycle, this should be written to the memory, to the data. And see the address there is 1111. And briefly we saw the data there. Right, so now we should be transferring from B to A. That's worked. And then finally we should be taking, we've got this address again, and the data has, yes, that was data. We've got 10 come back out. And then we should stop. Okay. Right, finally, we're not going to test the jump C just because I'm starting to run out of the will to do all these programs. But what we're going to do is we're going to write a counter. Um, so that's just going to check the infinite loop jump. And what we're going to do is A starts at 0. So we're just going to do inc A and then send A back to um, send that value back to the ALUX, and then from the ALUX to A, and then jump. So when we clear, it should set it to 0, so we don't even need to put that in. What's the op for inc? Incrementing at 0, 1, 0, 0, 0, 1, 0, 0. Got no data needed there. And then we're going to jump back. No, we're going to copy from ALUX back to A, which is 1, 1, 0. And then we're going to do our jump, which is we're just going to use the infinite jump. Actually, what we'll do is we'll do this with the infinite jump, and then we will do it with the carry jump, because what the carry jump should do is it should stop when we get one cycle done. So we will test both of them. So a jump is 0, 0, 1, 1. And then that'll be full set. So that feels better. Right. So first thing we're going to do is make sure we're not in run mode, and we're going to do a full clear. And we're going to set our memory address down to 0 and enter manual entry mode. And we're only putting ops in 0, 1, 0, 0. 0, 1, 0, 0, right to op memory. And then next data address 1, 1, 1, 0. Change the address 1, 1, 1, 0, right to op memory. And then finally the jump 0, 0, 1, 0. 0, 0, 1, 0, right to op memory. So that should be, it's only 3 lines, that should be a counter, and it should go on forever. Let's also, whilst we're at it, we're just going to double the clock speed. And we're going to watch A. So we start, actually should do the inc first, and then it's got 0, 0, 0, 1. And then it should jump, so we should go back and inc, and then it should go to 0, 0, 1, 0. It's halted. And why is it halted? That's a very good question. We didn't. Our address seems to be 0011. So I'm not quite sure what's happened. Our jump should have been 0011. I think we put the program in incorrectly. So let's start again from scratch. And actually, this needs to be 0000, the data to tell it where to jump back to. Oh, no, 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 no. So let's start again with this by doing a full clear and taking our address down to 0. And we're going to make sure our manual data is at 0s, because we're going to want to put that in at some point. So 0, 0, 1, 0, 0. 0, 1, 0, 0, right to op memory. Change, no, 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 we want to be in manual entry mode before anything can happen. There we go. Right, change the address. What's the second command? 1110. 1110. And then that's the new address. And it's 0011. Right to op memory. And make sure that we write that to the data memory. Although it probably is zeros anyway, it should be. Try again. Hopefully this is going to go around this time. Right, so first time ink A, second time we're going to get a 1 out, third time, it should jump back. Let's look at the program counter. Yes, it's 0. A goes this time. Yes, to 2. And then we jump back. So we can watch A to watch the counting, and we can watch the lights of the PC, the program counter, to see it keep going round. And we proved that it's going round. I'm not actually going to let it run all the way up because we know that it's not using that condition um, with C. Yeah, we got the jump the wrong way around. It says jump C. So if we've got a carry, it'll jump. And maybe it should have been jump not C, but we've got jump C. So what we're going to do to change our program is that instead of having is that we're going to move this jump down 1, and this would have been a way to test this, and then jump C is going to go to 0, 1, 0, 0. So this jumps past the program so that it stops, and it's 0, 1, 0, 1. 0, 1, 0, 1. Have we not got all the way through yet in that counting? We probably have, actually, because we're cycling round, aren't we? So let's stop running and enter manual entry mode. The first 2 lines are the same, so we don't need to alter those. We've already got the address in for the first one, so it's going to be 0, 1, 0, 1 and 0, 1, 0, 0. So 0, 1, 0, 1. And to jump past, it's going to go to 0, 1, 0, 0. Why is that not going in? In manual entry mode. Let's take that off. It has it gone in? I expected lights to go on at this point. Simulation stopped. Okay, so something's happened. We'll have to re-enter all our program. So I don't know why that's been the case. Full clear. There might have been a bus contaction somewhere. I might have switched something on when I shouldn't have done. I'm in manual entry mode. Let's start with the address down at zeros. So 0, 1, 0, 0. 0, 1, 0, 0. Right. Then 0, 0, 0, 1 address is 1, 1, 1, 0. 1, 1, 1, 0. Write that in. Go to the next address. And this is our new one, 0, 1, 0, 1. And I'm going to jump to 0, 1, 0, 0. 0, 1, 0, 1. And just double check that that is jump C. Yes, so write that to op memory. We've already got that in there, so let's write it to the data memory. And then finally, that memory address there, 0, 0, 1, 1 for a jump. And we're going to jump to the zeros. Right. So this should count up to 15 and then either stop at 15 or stop at 0. I can't work out in my head which. Let's do a reset. Oh, flipping heck. I've got full clear on. So that will have been clearing everything as I put it in. Once again, let's put this stuff in. Manual entry mode. 0, 1, 0, 0. You might know this by now. 1, 1, 1, 0. 1, 1, 1, 0. 0, 1, 0, 1. 0, 1, 0, 1. And I remember the address that we need is that. And then finally 0, 0, 1, 1. me to put zeros in the data memory. Touch wood. And run. Right. And I didn't switch off manual entry mode. So that has stopped the simulation, which has cleared everything. Oh dear. Take off manual entry mode. Do a full clear. Once more from the top, my dear friends. Stick with me. Hopefully we'll get this counter 0, 1, 0, 0, 0, 1, 0, 0. We've got our address at zeros. Right to op memory. 1, 1, 1, 0. 1, 1, 1, 0. Right to op memory. Go to the next address. 0, 1, 0, 1. 0, 1, 0, 1. Stick that in and that address in. And 0, 0, 1, 1. How many times am I going to need to do this? 0, 0, 1, 1. Right to op memory. Zeros into the data memory. Take off manual entry mode. Do a reset but not a full clear. And run. There's a 1 appeared in A. It is running. And it is cycling. Is it cycling yet? There. It's cycled back to zeros on the program counter. So the numbers are coming up through A. Finally, it seems to be running. So the only thing that we haven't tested yet is the jump when we get a C. The C overflow should happen when we try and ink when our A is 1, 1, 1, 1. It will still transfer that number into A, so it should get all the way back to zeros before then it jumps out and stops. And if all we wanted was a counter, then really this would be a very ham-fisted way of going about it. It's just a fairly handy little program to use to show the running of this 4-bit ALU CPU. I hope if you've been playing along with me that you've got this working and you've managed to get it so that it's programmable. What I'm not intending to do is extend this. At the moment, I might do in the future, do some stuff about programming in assembler, which is pretty much where we're at, except we're actually doing it directly into machine code without even using an assembler language to tell us what's happening. But that's kind of the next phase of this progress of understanding what's going on in computers, is to start doing some assembly programming. But I do hope that if you've been playing along, it has given you a much better understanding of what's going on inside a processor. Processors are different from each other, as I've said several times in the past. One of the major differences from many processors in this processor is that we don't have a stack register. So if you know what you're talking about with processors, you might have noticed the lack of a stack here. And the reason for that is simple, which is that we've got enough going on, and we don't have the space in our opcodes to be able to add stack functionality or in our memory. And if you didn't know anything about logic gates and Boolean logic, and you followed all the way through, and especially if you're a first-year Northumbria student, so you've started at the very beginning and gone through all these videos that I provided. I think the full count is 79 at this point, and the count of the videos that start with this with the simulator from to create this CPU is 55, I believe. That's a lot of watching and a lot of doing. It's been a lot of making and a lot of talking on my behalf as well. But well done for getting this far. This is well above what you're expected to be at first year level. Uh, but I hope you've found it interesting and useful. And if you're somebody else, uh, not one of our students, and have come through this process, then I hope you've enjoyed it, and I hope it's been useful for you for your learning. Uh, I feel like I've nearly finished things to say, which is good because the process is about to hit 1111 on A. So let's start talking about what it's doing. It should be tracking along, and the next thing we should get is the calculation of the C flag has gone. We should now get the go back to 0, and the next thing should be that this jump happens. And we've jumped to 0100 in our program, which is actually past the end of the program and stopped. So our program counted up to 15 and then went up to 16 and then stopped, and it does exactly what we imagined it would do. And it feels like, to me at least, it feels like a kind of magic that we've started from the basic logic gates, or these Boolean ideas of and or and nor and not, and things like that. And we've managed to create something that is programmable and will do what we want it to do. And now it's kind of up to the programmer to decide what they want it to do. Um, you can imagine that in the history of computing, the discovery or the creation of these ideas of how this thing might work has been a phenomenal step forwards in our society as a whole. And you've just had an insight into that process. So I hope you've enjoyed that. Um, that's it from me for now.